Well, you've made it through the test, hopefully. I gave you from last Thursday through Monday to finish the test, and hopefully you've had a chance to do that. That's plenty of time and to catch up on some of your homework if needed. Now we're in the final stretch now. This is the final exam test review, and this will be on for Tuesday, April the 28th, and Wednesday the 29th, and Thursday, the end of the week for us, the 30th. There'll be three lessons for the exam review, and then next week is the final and you're done. So you're really close to the end now. So let's start here, and again I'll go along and show which questions are omitted. It's a 50 question test, but we admit 5 or 6, I don't remember exactly, but it'll be about 45 questions. And you'll have a whole week to do it, 5 days. So here we go. Question 1, find the area in each polygon. Now notice that first A, B, C, D in this figure is a parallelogram. Notice the parallel lines, and so we see that the top A, B, and D, C have an equal length of 8, and then we have a height there for that parallelogram of 9. So we can easily say that the area for that ABCD parallelogram is base times height, or 8 times 9 is 72 centimeters squared. Now for triangle DEC, the top triangle, we have just a standard triangle formula, 1/2 base height, and it's 1/2 8, because DC is 8, and then we're seeing that the height for DEC triangle is 3. So we have 1/2 8 times 3, or that would of course be 12. Okay, now for the AFCD trapezoid, AFCD, notice that is the whole base of the big triangle, and then DC is the top part of the trapezoid. Now notice that DC and the bottom AF are parallel. That makes it a trapezoid. So here we go, 1/2 height B1 plus B2. So what we have is 1/2 times 12, because the height is 12, and then the base is 8 plus 24. So we have 1/2 12 is 6 times 32 is 192 centimeters squared. Now for the next one, we have some different kinds of quadrilaterals here, which we say we're supposed to classify each quadrilateral as specifically as possible. If HL, which is at the very top down to the next one on the center line, equals LM down to the center line across JG, and then also NK from the bottom up of the big quadrilateral is 6 also. So first of all, we want to find quadrilateral GLJN. Okay, so that's the kind of the inside quadrilateral of the big one. So this is a kite, and we can tell that because the diagonals bisected. Well, that's the kite. But anyway, it's 1/2 diagonal 1 times diagonal 2. And so we have 1/2, 8 plus 8 is 16 for one diagonal, and 6 plus 12 there is 18 for the other diagonal. So we have 16 by 18 across, and our formula for that quadrilateral is 1/2 times 16 times 18, or 128 square feet. Now for the quadrilateral GHJN, which is going from G on the side up to the top, down to the right, and then down halfway to the bottom, is a rhombus. And we know that because for the rhombus, diagonals bisect each other. Okay, so for that we have GJ being 8 and 8 on either side of HN, and H to M is 12, and M to N is 12, so we truly have diagonals bisecting each other. So again, we have 1/2 diagonal 1 times diagonal 2, or 1/2 24 times 16 is 192 square feet. Now for problem 3, we're going to classify each triangle as acute, right, or obtuse. And looking at the bottom here, this is our reminder for our formulas. If the longest side squared is greater than, that's a mistake, it should be greater than, the side 1 squared plus side 2 squared, it's obtuse. So if the longest one is greater than the other two side squares, it's obtuse. Now remember, the right triangle formula, of course, is if the longest side squared equals side 1 squared plus side 2 squared. We know that one. So then if the longest squared is less than the side 1, 2 plus side 2 squared, that makes it acute, and that makes sense. So the longest is greater than for obtuse, equal for right, and less than for acute. So let's look at our two examples here. So 3, 6, 8. So 8 squared is the longest, and we compare it to 3 squared plus 6 squared. So 64 is greater than 9 plus 36, which is 45. So that one would be obtuse. Now when we have 6, 6, and 3 squares of 3, we don't really have a longest side, we have a tie, but we still have to take one of the 6's and treat it as longest. So we have 6 squared compared to 6 squared plus 3 squared to 3 squared, and by definition has to be less than, because 6 squared plus 3 squared turns out to be 36 plus 3 times 3, 9 times 3, or 36 plus 27, and clearly 36 is less than 63. Now for problem 4, show that one leg of a right triangle is square root of 3 times as long as the second leg if the hypotenuse is twice as long as the second leg. Now we did a lot on this, so hopefully you remember. So if we call A the first leg and B the second leg and C the hypotenuse like we normally do, then using the Pythagorean theorem, A squared plus B squared equals C squared. Now using the fact that we're given that the hypotenuse is twice the shortest side, then A squared plus B squared is equal to 2B squared, assuming that B is the shortest side. And then we can subtract B squared from both sides, leaving us with A squared equals 3B squared, or square rooting both sides. A is equal to the square root of 3B, which is what we wanted to show. And if you remember, that was indeed how a 30, 60, 90 triangle worked. Now again, on 5, we're going to use our 30, 60, 90 triangle again, as we'll see. So find each measure of a regular hexagon, n equals 6, with sides of 40. Now, first of all, the central angle for the 6 triangles that we can make inside or as a part of the hexagon is 360 over 60. Now, I always use, we've used so much in class, the bottom of the 6 triangles, and so we always cut that angle, the central angle, in half, so we work with half of it, which is 30 degrees there. And noticing above that the sides, it's an equilateral triangle, so we have the two sides, and then we're only going to use half of the base for our right triangle, which has a top angle of 30 and a leg on the bottom of side over 2, because we're bisecting it. So remembering that our apothem is square root of 3 over square root of 3b, which is square root of 3 times s over 2, or square root of 3s over 2. So now we've had a formula that we used several times back when we did this a lot, which was A is equal to s over 2, that base, times the height, which is the apothem here, which is square root of 3 over 2s. So therefore, the area is square root of 3 over 4s squared for that bottom triangle of the hexagon. So now we can say the area is 6 of those triangles, which is square root of 3 over 4 times 40 squared, because 40 was the side. Now that comes out to 2400 square root of 3 square centimeters, and that's fine. Now finding the apothem, we take it as A from the area formula for polygons, regular polygons. We take A is equal to 1/2 apothem times P. We know the area from above is 2400 square root of 3, and then we have times 0.5A times 6 times 140, okay? And so, therefore, we have 0.5 times 6 is 3, 3 times 40 is 120, so we can divide both sides by 120 and just be left with the apothem, which is what we want, and have 2400 over 120, which is just 20 squares of 3, okay? Now we said we'd omit problem 6, and now for 7, we want to identify each line segment or angle in circle O. Okay, so this has a lot of things going on. So AB is a secant line. Notice AB cuts through the circle and goes on up to meet the other tangent line, but the other DC is a tangent line and AB is a secant line, and they meet up at D. So we're asked to just identify each thing, but AB is a secant line, PR is a chord because it's just within the circle at the bottom. Angle COQ is a central angle because O is the center of the circle, and angle BRP is a inscribed angle, which would be half the measure of arc BQP. So all we needed to know there was that BRP was an inscribed angle. So we were just identifying things. So now on problem 8, we look on the same problem. That's why I squeezed it in here. Didn't want to have to redraw that circle with all the lines through it. So the measure of OCD is where the radius meets the tangent at the point of tangency, and that was one of our theorems, that angle is equal to 90. And OQ is the hypotenuse in that little triangle, which is OP is the same because it's a radius, and we know that we're given up top if PX is 15, and OX is 8, then we can say that OP is equal to OQ because they're both radii, and that way we can get OP is the square root of the 8 squared plus the 15 squared equals the square root of 625 plus 264 plus 225, which would be the square root of 289, which is 17. So OP or OQ, both the same, is the radius is 17. Now the measure of ABR is equal to, the measure of ABR, we're given a condition, which we have to have. If the measure of arc of ABR, so the arc of ABR coming all around forming most of the circle is 320, then the measure of arc AR, which is all that's left, is 360 minus 320 is 40, and the measure of ABR, then the inscribed angle, is 1/2 the measure of the arc, and that's 1/2 of 40 or 20. Now the measure of APC, the arc APC, find the measure of ADC if measure of arc AB is 70 and measure of BC is 1/10. So we can get all the way around from A through B through Q through C, and that gives us 180 really. So it's the measure of arc APC is equal to 360 minus the 180, which is 180. Therefore the measure of ADC, now ADC is going from all the way up there to the top where the tangent line meets the secant line. Okay, so ADC is equal to 1/2 180 minus 110 or 70. Okay? Now on problem 9, find each measure if CB and CD are tangent to the circle A. So CD, if CB equals 18. Well, if CB equals 18, then we had a theorem that if from a point outside the circle, if two lines form tangents to the circle, then they must be equal. Okay, and so that means that if CB is 18, then CD is 18, because that's our theorem. Now the measure of BD is equal to 180 minus 80. Okay, so BD, because EB is 180, or EDB is EDB is 180, and if we take from that ED, which we're given as 80, then we know it's 180 minus 80 is 100. Now measure CDE. CDE is that angle inside, and we can say that that's 1/2 of 360 minus 80, or 1/2 of 280, which is 140. Okay, so that gives us that one. And then to find measure of BCD, we have to find first measure of arc BED going around the long way, 180 plus 80, which is 260, and that leaves the measure of BD to be 100, because 100 plus 260 is 360. Then finally we can get the measure of BCD is 1/2 the 260 minus the 100, that's how we found those kind, equals 1/2 of 160, or 80. Now in problem 10, it says find each angle if arc for MN equals 50 degrees and arc for PQ equals 30. So first of all, the angle MON is the internal angle where we add. So 1/2 the sum of 50 plus 30 is 1/2 of 80, or 40. But MOP is also an internal angle, but it's 180 minus the MON, which we just calculated, which is 180 minus 40, or 140. Now on 11, A is a point of tangency on B, so there's A, which is tangent, and find angle XMZ, X is up by the 80, XMC all the way back to M, which is the point outside the circle. Okay, so XMC would be 1/2 of 80, the arc on the outside, minus 55, because we subtract them when the point goes outside the circle. Okay, so that's 1/2 of 80 minus 55, 1/2 of 25, or 12.5. Now find the measure of arc AZ, which is all the way AXZ, we could even call it, if measure AMZ is 30, so that whole angle from the tangent point A back to the point outside M back to Z is 30, and measure of AW equals 70, then the measure of AMZ is equal to 30 equals 1, because we know AMZ is 30, is 1/2 AMZ equal to 1/2 measure of arc AZ minus 70. So we can multiply both sides by 2, that's what I saw there, the 2 times 30 is 60, and the 2 times 1/2 was to clear out the 1/2, so we had to multiply both sides by 2. So 60 equals the measure of arc AZ minus 70, and adding 70 to both sides, we have the measure of arc AZ is 130. Okay, on 12, we're asked to find the perimeter of a sector with an area of 4 pi over 3 inches squared if the circle's radius is 4 inches. So our area of a sector formula, this makes sense, is theta over 360 pi r squared. So it's just that fraction of the whole area, pi r squared. Well, we're given what that area is, 4 pi over 3, and we know that the radius is 4, so that's equal to theta over 360 pi times 4 squared. Now noticing the pi's cancel, and we're left with 4/3 is equal to theta times 60 over 360. So now to get theta, we multiply 4/3 times the reciprocal of 360 over 16, And 4 over 16 on one diagonal simplifies to 1/4, and 360 over 3 simplifies to 120. So we have 120 over 4 is 30 degrees for the angle sector. Now the length of the arc is same difference, but it's a fraction of the circumference. So L equals theta over 360 times 2 pi r, which is the circumference. We know that the central angle is 30, so 30 over 60 times 2 pi times 4. So 30 times 2 is 60 over 360 times 4 pi, so 60 over 360 is 1 over 6, and 4 pi over 6 simplifies to 2 pi over 3. So that's the length of the arc for that central angle. Now the length of the sector is just the length of the arc, which we just calculated, plus 2 radiuses, because we have a radius on one side, then the arc, and then the radius back to the center. So it's 2 times the radius 4 plus 2 pi over 3, or 8 plus 2 pi over 3, for what we were asked for, the perimeter of the sector. So that's really the final answer. Now, on 13, we're asked to write the standard form equation for the circle. So we're given x squared plus y squared plus 8x minus 12y equals negative 43, and we're going to have to complete the squares for x and y both. So we reorder them, putting the x's together and the y's together. So we have x squared plus 8x plus complete the blank 8 over 2 squared, which is 16, for the blank x on the right side. And then we take the y squared minus 12y plus completing the square minus 12 over 2 squared, or 6 squared, for the blank y, so we add the 36 over. So now, having completed the square, we take x plus 4 squared plus y minus 6 squared equals 16 plus 36 is 52 minus 43 is 9. And so that gives us a center of opposite sign, negative 4, 6, and radius r equals 3. Now we also omit 14, and then the last one we'll do for today is state the number of faces, edges, and vertices in a hexagonal prism. Remember, 6 sides. So there's 6 sides on the bottom that go straight up from the vertices on the bottom to a hexagon on top. So the hexagon on top and bottom, and then 6 sides coming up around it. So for the faces, we have 6 sides plus the top and the bottom is 8. For the edges, we have 6 up and down, 6 on the bottom, 6 on the top for the top and bottom hexagons, which is 18. And for vertices, we have 6 on the top and 6 on the bottom for 12. So we have F is 8, E is 18, and V is 12. So putting it into our Euler's formula, we say V minus E plus F equals 2, or 12 minus 18 plus 8 is negative 6 plus 8, or equal to 2, which it must be. So that's a check on our work that we did it right. And that's the end of today, April 28th. So keep up on your work, and you're near the end now. So just praise God, we're almost through with this class.